Hi everyone, I'm Pranoti, host of Under the Microscope. This series is brought to you by the Real Scientists Nano team. Our goal is to provide a platform where scientists can communicate their work and interact with the public. With that in mind, every week we introduce you to a scientist working in the field of materials or nanoscience, who tweets from the Real Scientists Nano Twitter account, which is realsci_nano. Hi everyone, my name is Pranoti, and today we have with us Yonatan Calahorra, who is an assistant professor at the Technion Israel Institute of Technology in Haifa, Israel. Hi Yonatan, how are you doing?
Hi, Pranoti. Thanks. Good to see you again.
Good to see you too. Long time no see. Let's get started. Let's dig right in. Could you tell us about your career so far? How did you end up being the assistant professor at Technion Institute? Do tell us. Where did it all start?
Yes. So I started my undergraduate studies in electrical engineering here in the same institute, actually at the Technion, which is very different as you know most grad students know. It's very different than what you would do later on in research. But I did develop this interest in the more physical and materials part of electrical engineering, which focused me towards semiconductor-based courses. Later on, after a brief intermission, I joined a nanoscience lab, but also in electrical engineering, where I've done work mostly on silicon nanowires, and mostly on studying their mechanical properties. And that was interesting, I guess somewhat a hint for me that I have this tendency to stumble upon fields which I don't know well yet.
Right.
As an electrical engineer, I had to study basically beam theory, and I ended up actually the most useful papers for my or some of the most useful papers for contributing to my master's came from civil engineering. Some of them from
civil engineering.
Yes.
Oh wow.
Yeah, because my study was basically suspended silicon nanowire beams, which I used an AFM tip to push. And a lot of the physics is similar to a concrete beam under load or under a point.
No way.
Yeah.
Oh my God, no way.
Yeah.
It's like two different worlds. Concrete is a macro material or a giant material, and if we are talking about AFM tips, this is like nano material or micro material.
It was amazing. It was amazing. In some of these silicon nanowire beams they were actually an arch because of some of the side effects of the process we used to make them. And when you apply a point load to an arc, it has different properties, different mechanical properties than what happens when you apply it to a straight beam. And actually the model that I found that was about 50 years old was pretty good at describing what was happening.
Okay.
Which was, it was, and it was from that world of, yeah, it was quite a learning experience. It was quite amazing.
Wow.
Yeah.
Sounds quite exciting. Please go on.
And following that, for my PhD, I really love this nano world, so I joined a group that had growth abilities, and we ventured on semiconductor nanowires from the 3-5 family in the growth, which was new, both to me, but both to and also the professor and the growth engineer. That was a lot of fun times. And, again, it's a new, right? For me, it's a new topic. It's real material science, actually, crystal growth. But it was also a challenge in the point of view, in a scientific point of view, because that was roughly 2010, and the nanowire world really picked up 10 years before that.
Correct.
So it was hard for us to create novelty.
Right. The field was getting more and more mature by the time you started with the growth of the nanowires.
Yeah. And that's something, you kind of always keep in mind, and when you start something new, you always pay this toll of entry, and you're not well rewarded.
I like this term of you pay this toll of entering a kind of mature field. I like that terminology. I'm going to use that in the future.
Yeah. So it was very interesting time, and I think because of that, we ended up doing a little bit of crazy stuff. For example, there was a very beautiful work where I was sort of second chair, was by a colleague, where we ended up growing nano flags. So usually you have nanowires where they grow from a catalyst, and it's called bottom up. The catalyst becomes saturated with the growth precursors, and it starts to build a nanowire, basically like to build a tower with a crane.
Correct. Right. Yeah, you're right.
Because the tower carries the crane.
Right. Correct.
So it's very high. So, but doing some manipulation during the growth, we managed to get the catalyst to sort of go or leave the top of the wire and go along the side, and then start to grow sideways, and have some non-catalytic growth, which ended up looking like a little sail. So it was like a nano flag or a sail. So I will definitely tweet those.
Please do, because that sounds so fascinating that the catalyst particle is coming down and there's a branch that is growing, and I want to see that. I definitely want to see that. Please.
It was a beautiful work headed by my colleague Sasha Curley. He's now outside academia.
Okay.
I also started to experiment with shaping the catalyst, taking it to different kind of extremes, trying to make it not round. Also turned into some nice and funny looking nanowires that grew from it.
Pictures, please.
Yeah, I will. I really like those. So yeah, coming back to the start, it's sort of how it was sort of our way to find the novelty, even though we were lagging behind in many ways, definitely behind the leading groups. Then I finished my PhD, and I was looking for a postdoc where I thought, what's the direction I want to take, and if that's an academic direction, what will I want to bring back with me to the Technion or anywhere else in that perspective. And I sort of realized that I want to move away from this world of semiconductor nanowires. Learning how establishing work with them is very hard, just starting. And also with the constraints of current interests in the scientific world, which we all have to follow in some ways. And I joined a group of Sohini Karanarian in Cambridge, which was focused. It has actually many focuses today. At that time, about 5 or 6 years ago, was focused a lot on mechanical energy harvesting. And that was very interesting for me. And that's how I became interested in the world of piezoelectric materials, ferroelectric materials. So another step in my evolution, or another new topic for me.
Another feather in your cap in the world of material science.
Yeah.
Wow.
Then I spent some time there. We were studying what happens to PVDF at the nanoscale. PVDF is a ferroelectric polymer. It's a very well-known material, but what happens to it at the nanoscale was not known at that time. For example, if you confine it to a tiny space, it likes to self-pole. Ferroelectric materials usually need electric poling for them to become, say, or to have the preferred polarization that they have.
Correct.
But there were then evidence that this can happen just by size confinement, which is very interesting. And I've spent some time doing that kind of work. A lot of work in the AFM to study these the piezoelectricity of these materials, which also brought me to think about some challenges you have while studying nano objects in AFM, and particularly in contact mode AFM. Basically, these objects move or break. So I had to develop some methods to overcome that.
Okay.
And at that point, I tried to sort of marry the topics that I was more familiar with, the world of semiconductor nanowires and semiconductors, with piezoelectric materials, and I began to became interested in what happens to this kind of materials under mechanical stresses. And now actually it's a very big topic of interest for me. And I was also exposed to another branch of electromechanic material. Piezoelectric material is their coupling to magnetic material. And this really blew my mind.
Oh wow. Okay.
Yeah. I mean, this, and then I met many things connected, right? Because sometimes you think about a transistor or a diode just as an electronic component, but it can actually be sensitive to other excitations coming from different physics, right? It can be sensitive to you applying stress to it, you applying heat to it, you shining light on it. And some of these are of course, very well established, but some are not. And in the world of composite magnetoelectrics, the magnetic phase and the electromechanical phase, magnetomechanical phase and the electromechanical phase are coupled by their mechanical properties.
Right.
And it has very interesting aspects to it. And so sometimes I like to, when I explain to undergrads or people about composite materials, so I like to give examples like you think about people in the train station where they play all the instruments, right? They have the harmonica and they play the guitar, and they also use the leg to drum. So that's very impressive, right? But obviously they are not the best at any one of these.
Right.
But a band of experts,
right,
they achieve a similar goal, but probably better.
Right.
So a
Correct.
composite material is kind of like that. You choose two good materials and put them
Right.
together and try to get the best of both worlds.
Good. Correct. Correct. Okay. All right. Yeah.
So yeah, so this kind of takes some of what I did and put it together. And this is my main focus now in my.
Okay, that sounds interesting. That's quite a journey you've had. Um, your current research, I mean, you spoke about this a bit in the short podcast, but where does it fit in this big picture of materials and nanoscience? I mean, your current research at the moment, because you have gathered a lot of experience with different materials, with the growth and the characterization, tiny materials, concrete, everything. So your current research, where does it fit in this big, wide puzzle of materials on nanoscience?
Yeah, I have a bit of a problem. It's very hard for me. Maybe it's not. Maybe a lot of scientists are like that. It's hard for me to say no, to say this is not interesting. And because I'm interested in basically in coupling between two properties, my research can take many forms. So it can take the form of covering a semiconductor or a semiconductor device with a magnetic layer and trying to use that to drive that device or to affect the way that device is working. But also, I could be interested in other materials that have interesting electromechanical coupling, like biomaterials, for example, and the way their properties can be manipulated through mechanical deformation. So the projects in my lab are quite diverse in that sense, which has a lot of advantages and disadvantages.
Okay.
Yep.
Right. Yes, that makes sense. And I think you're right. A lot of scientists have this problem of saying no, not being able to say no to interesting projects, even if it doesn't completely fit with what you're doing. I completely understand it. So it sounds to me, Yonatan, you have been interested or you have been involved in a lot of interesting research projects with the flags and with the beam, like the concrete beam and the AFM, and also your current research. So this question is a tough one, okay? If you have to pick one research project that you're most proud of, or the most fun or quirky one, could you pick one and explain it to us in simple words in the section we call In Other Words? It's a toughie, I know.
It's tough. A fun one would be, and I plan to tweet these pictures. It's one that I mentioned earlier. So at the point where we're growing these nanowires, it was indium phosphide usually, using gold catalysts. And the normal thing that people would do in order to achieve gold catalysts, maybe three things. You could disperse gold nanoparticles. That's very easy to do, and you get this grass of nanowires. You could deposit a thin layer of gold, heat it up, and it agglomerates to nanoparticles and grow a grass. Or you could use some lithography and have this array of more ordered wires. Usually e-beam lithography gives you tiny dots, and you can use that.
Right.
And I became interested in the question of what happens if your particle is not circular.
So the catalyst particle is not spherical or circular.
Yes, but the problem with that is that when things happen, at 400, 500 degrees, then metals, well, not all maybe, but definitely gold, it's sort of liquid, or it's a liquid solution containing some indium.
Right.
It likes,
to
liquid,
be spherical.
They don't like to have asymmetrical shape. They reduce their energy.
Yeah.
And I was thinking, how to do it. But because we previously developed a sort of selective area method, which combined metal particles and a mask. We basically had our particles in a mask of some silicon nitride, something like that. Mm-hmm. And then I said, okay, so what will happen if I will not use lithography to define dots, but rather I will use it to define stripes. Mm. And in these stripes, the gold will agglomerate, but it will not be able to form a sphere, and it will form something that's more elliptical.
Mm-hmm. Correct.
So that's kind of a geometrical thing to do, and
right.
then it actually worked after maybe 1 or 2 tries. Uh-huh. And I managed to get elliptical particles, and then I managed to get them to grow wires. Ah. And these wires, some of them, most of them, when it worked, they had asymmetrical cross sections. So they were no longer nice looking. Usually it's hexagons. Mm-hmm. But now they had 2 different axes in the plane or perpendicular to the plane of growth.
Oh, wow.
That was pretty cool.
So you managed to bend the rules of physics and chemistry.
Yeah. So I kind of forced the particle to stay asymmetric or not to be circular. The interesting thing is that to a large extent, it would keep that way, because after growth is starting, it's sort of wetting the wire. And so it doesn't go to circular, at least not easily. Mm-hmm.
Correct.
But actually, and that was, so I was looking at these tiny wires or in the SEM, but actually what was even more interesting is that, the best thing is that you find something that surprises you. Mm-hmm. And because I patterned these stripes in different crystalline orientations relative to the growth substrate, what I found is that in particular conditions where these stripes were not or aligned in a specific way to the crystal, the wires that grew actually had 8 facets rather than 6.
Oh, wow.
Yeah. And that was, to me, was a complete surprise. Maybe because I'm experimentalist at heart, so I didn't think hard what I was going to get. But right. it was very common to think that the wires grow as hexagons, depending on the crystal structure, whether they're wurtzite or zinc blende, depending on the growth conditions that you use. Mm-hmm. But in this case, there was some energy compromise between their size, the facets that they want to grow, and the facets that it's convenient for them to grow because of the confinement induced by the stripe. Mm-hmm. And so 6 of these facets are of one kind, and 2 additional ones are actually of a different kind, a different type. And I didn't get to continue this work, but obviously they have, some different chemical properties. So it can be it is still very interesting for me, although I don't pursue it.
Yeah. I can imagine. Yeah. I can see why you picked this as the project, one of the projects. Yeah. That is the fun one.
It was, yeah. And maybe, take home message is that the best moment for a scientist is to look at the screen of something and look again and say, what is it? I don't get it. What am I seeing here?
I didn't expect that. What are you?
Yeah, and because at that time I was looking at nanowires for so long, I could easily count the facets in SEM, and I was looking and I was like, wait, 1, 2, 3, 4, because you're looking at from one side.
Right.
I'm saying, well, what's going on here? And then I look from the top. You can make that was one of the moments I really liked.
That
happens every now and then.
Yes, it does. It reminds me of this "What are you" moment when I was growing graphene by chemical vapor deposition during my master. And this was back in, when was this? 2014,
Mm.
something like that. And around that time, the centimeter large hexagonal graphene it was not the case. You had to look at it under the light microscope or electron microscope, not with the naked eye. You could never see them on the copper foil. And I managed to grow them, and I was taking them out, like I was taking my copper foil after the process, after the CVD run. I'm like, what are you? What are you dots? Like, why are there circular patches on my copper? And then I looked closer and those were hexagonal. And I'm like, is that copper? But that doesn't make any sense. Why does it look different? And of course, then I did Raman spectroscopy. I transferred it on silicon oxide substrate. I looked at it on the light microscope, electron microscope, and I was like, wow, this is graphene. I was in the clean room. I had to get out of my clean room gear, go to the park, like go to the grass, and be like, okay, did I just see graphene with my naked eyes? This is just
Ah,
no. Was it really graphene? Oh my God, that was so cool.
yeah,
So yeah, these discoveries are really yeah, I still remember that.
yeah,
And I hope you will talk about your discoveries and this project as well, and other projects as well, with pictures and everything when you're taking over the Real Scientist Nano Twitter account.
yeah,
Jonathan, it sounds to me that you love being a scientist. You are an experimental scientist by heart, in your heart. In addition to the research aspect of being a scientist, what else do you like?
yeah. Um, it's well, first of all, it's a little cheating, I guess, but at this position, uh, one thing I really, really like is talking is talking about science with my students,
Mm-hmm.
which you never know. I think before you do things, if you really gonna like them or not. But I find that this is actually the part of the job I like the most. Discussing results, discussing experiment, discussing future directions. So I hope we're a very young group, only 1 year, but I hope this will grow and grow. I like interacting with other scientists, hearing their perspective. You know, you get so much inspiration from other work. I mean, without these kind of things, I would never be doing what I'm doing, and you know, finding out new worlds.
Mm-hmm.
Yes, there's also teaching, which I like.
That's amazing. Okay. So there's a lot of other things you also enjoy that comes with being a scientist. That's amazing. And I really like that you mentioned you like teaching, because we need scientists who enjoy teaching in order to cultivate or bring up the next generation of scientists. So that's
Yeah,
really, really good. Jonathan, if I mean, I guess you have gathered a lot of experience and have learned a lot throughout your journey, so far at least, in being a scientist. But if you were to go back in time and talk to the younger Jonathan, what advice would you give him? Or what advice would you give to the students who are starting out today of their scientific journey? What advice or pieces of advice would you like to share?
yeah, it's a tough one because you always have limited time to do things. Uh,
Yeah, sure.
I many times I find myself a little sorry for things I don't know. For example, venturing now into the world of magnetoelectric composites, but coming from the field of well, semiconductors and then isoelectric. It's a challenge
Mhm.
to speak the magnetic materials language. I really wish I had more of a fundamental physics uh,
Mhm.
training. But of course, you never know. It's this balance of knowing what's happening now, what's the state of the art, but also knowing the basics.
Correct. Yes, definitely.
But yeah, the advice is yeah, read, read, and read.
inform yourselves, keep in touch with what's happening.
Yeah.
Yeah, that makes sense. Well, I hope that's a really good piece of advice for sure, and I hope you can share your other advice with our followers when you are taking over the Real Scientist Nano Twitter account. Yonatan, I hope, and it sounds definitely to me that your research experience so far has been wonderful and will continue to be wonderful in the future as well. I hope that. However, if you had 3 wishes to improve your research experience, what would you ask for? And I'm not promising anything here, okay?
Well, maybe one thing you can.
Maybe, let's see.
Yeah, I can talk about my challenges in this new role. It may be something that I will also expand on. It's this transition from being a postdoc to being the head of the lab, which people always say that we're not really trained to do it, and we're not necessarily good at what's needed. And what I find is that I would love to have more time to do all the new things I need to do. And of course, funding is a challenge. You need to you want to have more people, but yeah, you need to support them, the scholarship or the salaries, but also their science and their travel. I mean, you want them to develop, and also it's also cheating, but more time to read papers. There's so much happening now these days. It's almost overwhelming. It's very hard to know what's relevant. A lot of things, especially if you're working in a multidisciplinary field, which many people are these days, right? And keeping tab on the research is very hard. I would like to find a good way to manage that.
Okay. All right.
Yeah.
So those are your 3 wishes: more time, more funding, and efficient ways of keeping tab on the new research that is going on. Well, you said maybe one of the wishes, maybe I can grant. Well, I don't have the power to do any of that, of course. But maybe keeping tabs on the new research. There are probably some research intelligence tools that are being developed and that are available, and I hope you find them useful. I hope you find them first, and then I hope you find them useful. All 3 very important wishes, and I wish I could just grant them, not just for you, but for all scientists around the world, and also for myself, especially with more time. I could use some more time with all my multitudes of projects going on in parallel to my day job. However, I hope we are working towards it, at least with the more funding and keeping tabs on the new research, being more efficient there. Yonatan, it has been wonderful speaking with you. But before I let you go, I have to ask one last question. What are your learnings from 2020? Or let's put it this way: what are your learnings from the world that has become since the year 2020? And I'm not going to use the C word or the P word, but you know what I'm referring to.
Yeah, it's been tough. Of course, the first few months, I was still postdoc, family and everyone. Certainty, you have to be home with young children that don't have a nursery or school. It was very hard. I actually suspect that I and probably many others have not fully recovered from that time in terms of personal
challenges.
Yeah, like your ability to concentrate, basically, or at least mine. I think I'll come back. And of course, in terms of managing and handling your scientific career, travel has been affected. I think there's consensus that it's very hard to do the same things in online meetings as you do in face-to-face gatherings. I try when I attend online meeting to make at least one useful connection So I
The
feel
bar is that low.
so I feel it's not going to waste. Yeah,
Okay.
that's a very big challenge, but I think still the emergence of online is not completely bad, of course.
You just need to find a balance, I feel.
It's a matter of balance. So here in our department, so Israel is quite far from most of Europe, not to mention US, but for example, we managed to get good people to come and speak in our seminars.
Correct.
It takes very little effort.
Right.
But then again, the downside is that there's less meeting and less personal relations that develop from. Like everything, there's balance and pros and cons.
Absolutely. Absolutely. Well, thank you very much for being so candid and speaking with me about your learnings and everything that I was curious about, you as a scientist, you as a researcher, and your journey and everything. Very much looking forward to having you on Real Scientist Nano Twitter account. Thank you very much, Yonatan, for speaking with me.
Thank you, Pranati. It was a pleasure. Yeah, I'm looking forward to this week.
Thank you for listening. This is Pranati, host of Under the Microscope. To know more about us, visit our website, thesciencetalk.com, and follow us on Twitter at realsci_nano.